My name is Fateme Dashtia Hangar, and today I want to talk about a paper which it is not published yet, but it would be a perfect one, and it is under its revision. The UNETR++ delving into efficient and accurate 3D medical image segmentation, that it is about the 3D or volumetric medical image segmentation. To give you an overview of our talk, first I want to talk about the motivation and all the problems that are in this task. And we're gonna talk about the contribution, and next we will delve into the framework and methodology, and finally we will talk about the results and conclusion. When it comes to medical image segmentation, 3D or volumetric ones are the fundamental problem because of their numerous slides, but they have lots of application like tumor identification, organ localization, and so on. To do so, to do the 3D image segmentation, we typically use unit architecture that encoders generate hierarchical low dimensional of representation of a 3D image, and the decoder maps this learned representation to a voxel-wise segmentation. And these CNN-based methods use convolutional and deconvolutional in their encoder and decoder. But the challenge and the problem here is that because of their limited receptive field, they struggle to achieve an accurate segmentation result. On the other hand, we can also use transformer-based methods, which they are global and have a perfect performance. But the challenge and the problem is that we have this transformer, because they have self-attention mechanism in their structure. We have a computational bottleneck because the self-attention operation has a quadratic complexity. So we talked about two solutions for 3D image segmentation, and here's the third one, that design a hybrid architecture to combine benefits of both local convolution and global attention. But also we have problem in this solution, and the problem is that although it will increase the segmentation accuracy, however, the problem is that the model size is also increased in terms of parameters, flops, and so we will have unsatisfactory robustness, which in all of these problems, we believe that they are likely due to their inefficient self-attention design. So in this work, we want to simultaneously improve both segmentation accuracy and model efficiency in terms of parameters, flops, inference speed, in a single unified framework. So we propose UNETR++, which is built on UNETR framework and introduced a novel efficient paired attention block, EPA, that efficiently learns spatial and channel-wise discriminative features using a pair of interdependent branches based on spatial and channeled attention. Our spatial channel is in EPA block will project the keys and values to a fixed lower dimensional space, making the self-attention mechanism computation linear instead of being quadratic. On the other hand, our channel attention by dot product operation between queries and keys emphasize the dependencies between the channel feature map. Well, we will share the weights for query and keys across these two branches in order to capture a strong correlation between them, and also by doing so, we will control the number of network parameters. But on the other hand, we keep the weights for values independent to help learning complementary features in both branches. For related works in the CNN-based segmentation, we have several papers, several projects. For example, in military, I'm not sure about the pronunciation, but in military, this group proposed to use a 3D representation of a volumetric image by downsampling the volume to lower resolution for preserving the beneficial image features. And I'm so sorry about the pronunciation. The Kik et al. Extend the unit architecture to volumetric segmentation by replacing the 2D operations with their 3D counterparts learning from a sparsely annotated volumetric image. And the other group introduced a generalized segmentation framework. Its name is UNET, that automatically configures the architecture to extract features at multiple scales. And finally, the other group proposed a multi-scale 3D fully convolution network to learn representation from varying resolution for multi-organ segmentation. In transformer-based segmentation methods, we have two projects. First one, they divide the volumetric image, the 3D image, into 3D patches, which are then flattened to construct a one-dimension embedding and passed it to a backbone for global representation. And the other group proposed an architecture with shifted windows for 2D medical image segmentation. And the image is divided into patches and fed into a U-shaped encoder-decoder for local and global representation learning. As I told you, as I previously mentioned, we utilize both CNN and Transformer to have a hybrid segmentation. As an example of this method, the Hatamizadeh group, and they propose a UNETR that combine the long range spatial dependencies of transformers with the convolutional neural networks inductive bias into a U-shaped encoder-decoder architecture. The transformer block in UNETR are mainly used in the encoder to extract fixed global representation, and then they are merged at the multiple resolutions with the CNN-based encoders, the decoders. The other group introduced a better architecture. It is the best, but the problem is that it is very complex. The N-former that adapt the Swin unit architecture, the convolution layers transform the input scan into 3D patches, and volume-based self-attention modules are introduced to build hierarchical feature pyramid. But as I told you, it has a very good performance, but we have a computational complexity. I want to jump into the methodology for our proposed architecture, UNETR++, that is based on UNET, and it has two sections. A hierarchical encoder-decoder structure with the skip connection between the encoders and decoders. And the other section is followed by convolutional blocks to generate the prediction masks. Well, in this slide, the encoder's first stage consists of patch embedding to divide volumetric input into 3D patches, followed by the novel efficient PEPA, paired attention block, and the encoder stages are connected with the decoder stage via skip connections to merge the output at different resolutions. This enables the recovery of the spatial information lost during the downsampling operation, leading to predicting a more precise output. Instead of using a fixed feature resolution throughout the encoders, our UNETR++ employs a hierarchical design where the resolution of the feature is gradually decreased by a factor of 2 in each stage. Well, in EPA block, EPA is comprised of a spatial and channel attention module. The spatial attention module reduces the complexity of the self-attention from quadratic to linear, as I mentioned previously, and the channel attention module effectively learns the interdependencies between the channel feature map, and I will elaborate it on the next. For a spatial channel, we given a normalized tensor of shape. First, I want to talk about the EPA block. The input feature maps X are fed into the channel and spatial attention modules of the EPA block, and the weights of Q and key linear layers are shared across the two attention modules, and the different value layer is used for each attention module, as you can see in the equations. In the spatial channel, given a normalized tensor of shape HWT times C, we compute Q key and value by 3 linear layers. Then we project K and value from the high dimensional of HWD times C to a smaller dimension P times C. We called it the resulting matrix K project and V tilde. And finally, we compute the attention using the K project and V tilde, which have a lower dimension. This helps us improve the computational complexity in the spatial attention. And in the channel attention, in this section, we use the same query and key as we used in spatial attention, and we compute the value vector V by a new linear layer. Then the final output form the channel attention is calculated by the equation 4, and at the end we are going to combine the outputs from 2 attention modules by the equation 5, which is a simple addition and 2 convolutional layer. In the loss function, to train the network, we are going to use a loss function that is a summation of soft dice and cross entropy, which soft dice is a usual loss function for segmentation, and cross entropy is used for classification. And you can see the hyperparameters. For example, we have V number of voxels and Y grand truths at voxels V for class I, and the P's output probability at voxels V for class I. And here's the equation. The data sets used in this paper are, we have 5 data sets. Synapse data sets consist of abdominal CT scans of 30 subjects with 8 organs, and we have VTCV data set with 30 subjects for training and 20 subjects for testing with abdominal CT scans, and the ACDC data sets that it is a cardiac MRI image of 100 patients, and the BRAT data set that comprise of that everyone knows about the breadth, and the long data sets comprise of 36 CT scan volumes for a two-class problem, with the goal to segment lung cancer from the background. In evaluation metrics, to evaluate the performance of different models, we are using two metrics. One is DICE similarity coefficient, and the other one is 95 percentile Hausdorff distance. The DICE coefficient, the DICE similarity coefficient measures the overlap between the volumetric segmentation predictions and the voxels of ground truths, and you can see the equation in equation 7. And Hausdorff distance is a boundary-based metric to measure the 95th percentile of the distance between the boundary of the volumetric segmentation predictions and the voxel of ground truths. That is calculated by taking the max of two different distances. One is the DYP, that it is the maximum 95th percentile distance between predicted voxels and the ground truths, and the DPY, that is the maximum 95th percentile distance between the ground truths and the predicted voxels. Here is the training sets that talks about the GPU and other hyperparameters. I'm gonna skip it. For the results, so first, in the results, we are looking at the performance of our model over the Synapse data set, and we are comparing with the baseline, which is UNETR. As you see, when we add EPA in encoder and decoder, we get a better and better DICE score. And the second table is the performance on BTCB data set, which is for multi-organ segmentation. As you see, UNETR++ either has the best performance in each class or is very competitive with the best results. Here you are looking at some qualitative results, so that we get a sense of the output image that each model is producing, how they compare to each other qualitatively. For example, you can look at this white region that is mistakenly produced by UNETR, but UNETR++ doesn't have that issue. And also, if you wanna compare with N-former, you should look at this small region in the green area. This is a mistake by N-former, but UNETR++ is not creating that. And here are the final results on the last 3 data sets. And as you see, the UNETR++ has the best performance. And also, in particular, you can look at the performance on a Brad's data set, that the number of parameters in comparison to the other models, and you see that not only the UNETR++ has the best performance, but also has a smaller number of parameters. That's it. As a conclusion, we have UNETR++ introduces EPA blocks into the encoder-decoder structure of UNET, which encodes enriched interdependent spatial and channel features by using spatial and channel attention, shares the weights of query and key mapping functions to better communicate between a special and channel branch, providing complementary benefits as well as reducing the parameters. Achieve favorable segmentation results on 5 data sets by significantly reducing the model complexity with better speed and compared to the existing methods.